right, thank you, Ellie. Thanks, everyone. Thanks to the organizers for putting together this great school and for inviting me to speak. I am going to take the opportunity of being the first speaker to start a little bit with a broad brush. I'm not, let me make a comment now and then forget about it. I'm going to not mention too many references during the lectures, but I'll mention a few now. And I think Bruno just asked me to post my notes in a little bit, so I'll also do that. So let me mention just 3 references. So there's, of course, the Bible of the subject, which is the paper on generalized global symmetries. And then there are 2 reviews, one by John McGreevy from a condensed matter point of view, and one by Cordova, myself, Ken Intriligator, and Shuhang Shao from about the same time and a couple of years ago. So these have a lot of references, and I encourage you to go search there, but I'm also happy to answer specific questions. So let me just leave this up. All right. So let me start with something very general and very basic, which I'm sure you've been indoctrinated with on some occasion or another, which is that, of course, symmetries are important. That's why we're here. But they come in slightly different varieties, especially in elementary presentations of our subject. And it's important to distinguish them. So roughly speaking, we encounter 2 different kinds of symmetries. Maybe we encounter even more, but these are the 2 that we're sort of bombarded with early on. The first one is global symmetries. And the second one is gauge symmetries. And both are important, but they're very different. So what's the primary difference? The primary difference, in a nutshell, is that global symmetries act on something, and gauge symmetries do not act on anything. And so if you're a careful person or a mathematically inclined person, you would not call a gauge symmetry a symmetry at all. But in physics, we use this terminology, and we're kind of stuck with it. So we should be careful to distinguish it. So global symmetries act non-trivially on actual physical observables, things you measure. Expectation values of operators in quantum mechanics, like x. And so if you have a rotationally invariant theory, then x transforms as a vector, and the Hamiltonian is invariant under rotations. There's nothing wrong with the rotation symmetry being broken. It doesn't need to be there. If you add an external electric or magnetic field to the problem, then that symmetry is broken explicitly, and the symmetry is gone. There's nothing wrong with that. But if the symmetry is there, it tells you something. It tells you that states come in multiplets of the symmetry, and it relates matrix elements and gives you selection rules, so you learn something. And if the symmetry is badly broken, too bad. But if the symmetry is only broken by a little bit, if it's weakly broken, then we say that it's an approximate symmetry, and it's still a very useful concept. So there's lots of situations where that happens. For example, whenever we do perturbation theory, we assume that. There are famous examples in nuclear physics. For example, the fact that the proton and the neutron are nearly degenerate means that the isospin symmetry that relates them is only broken by a small amount. And that's very useful. And there are many, many examples like that. So global symmetries are useful when they're there, and they're useful even when they're slightly broken. Now, things get even more interesting when you graduate from quantum mechanics to field theory, because now you have a notion of locality. So in QFT, you have fields, just to state the obvious. And you have a notion of locality. And depending what kind of problem you're solving, that might be locality in space or locality in space and time. And you may or may not have Lorentz invariance. So there are different, there are stronger and less strong notions of locality. And once you throw locality into the game, the notion of a symmetry gets kind of enriched in a substantial way, because you can have an interesting interplay of the action of the symmetry with the local properties of the theory. So for example, the most conventional type of symmetry in quantum field theory, the one that's now called an ordinary symmetry or a zero-form symmetry, I'll explain what this is in a second, is something that doesn't act on space-time and transforms the field in some way. For example, if phi is some real field, you might have a Z2 symmetry that flips phi to minus phi. And this is what we used to call a flavor symmetry in particle physics. It's an internal symmetry. You could think of this as an Ising field, and this is the spin flip symmetry. And this symmetry acts on the local operators, right? This is something that you've all learned some way or another. But once you introduce this notion of locality, you can also generalize the notion of operators and the notion of defects. For example, in addition to considering local operators, you might consider operators that are supported on higher dimensional manifolds in spacetime, curves, for instance, surfaces. Curves are particularly natural in gauge theory because famously they're Wilson loop type operators, or maybe other type of loop operators that are important. So this is a familiar notion. And then you can consider surfaces and other things as well. And once you consider those type of observables, you can also ask what kind of symmetries act on them. And that very naturally leads you to the realm of generalized symmetries, higher form symmetries, higher group symmetries, and even more exotic things that you'll surely hear about. I will stick to these simplest generalized symmetries that I just mentioned. Okay, so this is roughly the arena in which we'll be playing, but let me contrast that a little bit with gauge symmetries. Gauge symmetries, as I said, don't act on anything, so the question is, what are they good for? Well, they're good for something, since we all need them and use them to various degrees. And the canonical answer why you need them, at least in particle physics, is because they're the most powerful and convenient way to construct Lagrangians or theories that are simultaneously local and Lorentz invariant. That's a perfectly valid answer, but it's a little bit too narrow, since gauge symmetries and gauge theories also play a role in many systems that are Lorentz invariant, for example, condensed matter systems. And they're typically emergent. Now, whenever it actually makes sense to talk about a gauge symmetry or a gauge, then it is always what is more properly called a redundancy. So it's something that you quotient out by when you do the path integral over some set of fields, and it's just convenient to introduce this redundancy in order to make manifest or make simpler various other properties of the theory, like locality or Lorentz invariance and things like that. So we need this in order to write down sensible theories, and sometimes we get it for free if it's emergent. But there are lots of cautionary words that one could spend time on. I won't spend too much time on it, coming from the fact that the notion of a gauge symmetry is just a redundancy and that it doesn't really act on anything. For example, it means that you can't look at a theory, look at its observables, and tell me what the gauge group is. That's possible in various limits. If you take various semi-classical limits or weak coupling limits, then you can sensibly talk about what the gauge group is. But in the abstract, you cannot do that. And that actually plays an important role in many gauge theory dualities, which typically relate gauge theories with seemingly different gauge groups. And sometimes dualities relate gauge theories to theories that don't have any gauge fields at all. For example, you could think of the pion Lagrangian in QCD as an example of that, where you have a gauge theory in the UV, and then the low energy effective theory, or the dual theory, is just a theory of scalar fields. Or you can think of particle vortex duality in condensed matter physics, which relates a abelian gauge theory to a non-gauge theory. So there are many examples like that. no matter what kind of branch of physics you come from, you have your own reasons to be interested in gauge theories, but because of the reasons I just said about gauge symmetry, the tool that will actually help us understand gauge theories better is not gauge symmetry, it's global symmetry. Because global symmetry actually acts on things and it has consequences, and we can use it to learn something about the theory. And, well, roughly speaking, there are many reasons why global symmetries are useful, but let me just mention two that are kind of all over the place. One is that the global symmetry of a theory is a very rigid structure. Once you know what it is, it's typically easy to convince yourself that it cannot be continuously deformed, that it's kind of inert under changing continuous parameters, inert under renormalization group flows. That means you can actually track this whole structure and all of its ancillaries, anomalies and SPTs and things like that, from weak to strong coupling, and you can try to learn something about a theory that would otherwise be unsolvable, and you couldn't say much about it. And the other thing that will be also important for me, because I'm kind of going to organize my presentation around the notion of gauge theory phases, is that symmetries are very closely tied to the notion of phase transitions. This is a famous by now, not something like 90-year-old idea due to Landau. Sometimes people call it the Landau paradigm, which is that the realization of global symmetries has something to do with phases and phase transitions. And of course, the prototypical Landau-style examples involve internal symmetries, zero-form symmetries acting on fields like this. For example, if you take the Ising model, either on the lattice or think of it as phi to the fourth theory in the continuum, then indeed this phi, this real field phi, represents the Ising spin, and there's a Z2 symmetry that flips phi, and then depending on what the parameters of your model are, that field phi might either have 0 vev or it might have a vev, and those two situations are very different. Right, roughly speaking, you can tune the potential to look either like this or like this, famously. So this is the symmetry preserving state, this is the symmetry breaking state. And in both of these situations, you can learn a lot from the symmetry. For example, in the symmetry preserving state, the symmetry is unbroken, so you can still use it to group fields and particles and things in multiplets of this Z2. Here you cannot do that in the broken phase, but you do learn something else. You learn that there's a domain wall connecting these two vacua. The presence of the domain wall is a kind of consequence of the broken symmetry. For the purposes of this relationship, the thing that I want to remind you of, and I think I even put a little exercise on it that you can look at later, is that because the symmetry is realized differently in these two regimes, right here Z2 is broken spontaneously, and here it's unbroken, there has to be necessarily a phase transition as you dial from one regime to the other. In general, when the theory is very complicated, you may not know what the order of the phase transition is. In the case of the Ising model, we do actually know what it is, pretty much in any dimension. But in general, you don't know, but you can say for sure that these two asymptotic regimes cannot be smoothly connected. So there has to be a sharp transition in between. And incidentally, I should say that the existence of sharp phase transitions and spontaneous symmetry breaking is also one of the things that kind of emerges once you go from quantum mechanics to quantum field theory in infinite volume. By the way, I should have said it at the beginning if it isn't clear, but you should interrupt me with questions at any time during the talk. No need to wait till the end. It's probably better if you don't.
Yeah. Why you define the global zero-form symmetry to be independent of space-time?
Can you repeat the question every time?
Why did I define a zero-form symmetry to be independent of space-time? Well, we can debate what the definition of a zero-form symmetry should be, but there are certainly space-time symmetries. You'll see that in some sense they're zero-form symmetries, and sometimes they're a little bit different. Space-time symmetries are always a little bit different. Yeah, they certainly act on local operators. Yeah, but this is just the particular symmetry that I was interested in. There are many others in this model. All right. Maybe just to jog your memory, and since I occasionally refer to it for comparison purposes, when we do higher symmetries, I'll try to make various analogies with the conventional case. Let me remind you of another very conventional example, but now with continuous zero-form symmetry, the O2 model. And we're not going to do this indefinitely. We're going to stop with O2, where you have a complex scalar field, and you take the Lagrangian of the theory to be invariant under phase rotations of phi, constant phase rotations of phi. So this is a U1 flavor symmetry, U1 zero-form symmetry, if you want. I haven't defined what a zero-form symmetry is yet. You should just think of it as an ordinary symmetry, the most conventional thing that you know about. And you can take the standard kind of U1 invariant phi to the fourth Lagrangian if you want, or something more complicated, as long as it preserves the symmetry. Now this, because it's a continuous symmetry, has a few features that the Ising model does not. First of all, it has a conserved Noether current. And the second thing it does, again, because the symmetry is continuous, is that if you consider the symmetry broken phase, so in other words, if you take this picture and you revolve it around the axis to make it U1 invariant, then the symmetry preserving phase is not very different, except that now you have an unbroken U1 symmetry, so you can classify states by their U1 charges. But if you look at the symmetry breaking phase, right, you have this wine bottle potential with the flat direction at the bottom. And that means that the low energy theory here is not gapped. There's a gapless Goldstone boson, Nambu Goldstone boson. So when the U1 symmetry is spontaneously broken, you get a massless Nambu Goldstone boson, which is associated with the phase of the phi field going around this minimum. And in this phase, roughly speaking, this J current becomes linear in this Nambu Goldstone boson. Right? So if you write phi as being roughly speaking some number, the VEV times e to the I pi, where pi is this Goldstone field, then up to a constant here, up to the pion decay constant, this is linear in the pion field. There are, of course, nonlinear corrections. But that means that when you act with the current on the vacuum, you create a single particle state, among other things, which is the Goldstone. And that's important. That's one of the many hallmarks of ordinary spontaneous symmetry breaking, very famously. And we'll see generalizations of this when we get to higher form symmetries. Very good. Any questions? All right. So one of the things which I'll say now, but I won't do until a little bit later, is that the existence of a current also enables us to couple this U1 symmetry to background fields. Right? We can couple this, take this current and add a term to the Lagrangian, which looks like J mu A mu, where A mu is a non-dynamical field, it's just a source. And that's a very useful thing to do, especially if you're studying things like anomalies or SPTs. And then if we wish, we could also gauge this symmetry and turn this model into a gauge theory. And we'll also do that. That's called the abelian Higgs model. And we'll discuss it tomorrow. All right. Maybe in partial answer to the question I got earlier, of course, if you take the Lagrangian of this field, or also the Ising field, to be Lorentz invariant, for example, if you take the standard phi to the 4 Lagrangian for both, then you also have Poincare symmetry which is a space-time symmetry. In some sense, it's a zero-form symmetry. In many ways, it's a zero-form symmetry. But the associated conserved current, of course, is not a one-form current like this. It's the symmetric stress tensor. So this is symmetric and conserved. And this is the stress tensor. Very good. Maybe a small comment I should make is that, well, I'll make it in a second. I haven't defined the charge yet. All right. So let me try to abstract from this simple example a few things about ordinary zero-form symmetries and maybe make a few more comments. So let me kind of remind you of some zero-form or ordinary symmetry basics. We've already seen an important part of that, which is that, at least for continuous symmetries, there are conserved one-form currents, vector currents. And of course, the thing that you are instructed to do when you have such a current, among others, is to construct a charge, which is obtained by integrating the zero component of that current along a spatial slice. So imagine that you are in a kind of Lorentzian signature. Time is this way. Here's space. And then you can integrate that current, the zero component of the current along all of space. That's a Lorentz scalar. And by virtue of current conservation, it commutes with the Hamiltonian. So it's conserved in the conventional sense. Now, one very useful generalization that is most appropriate in Euclidean signature, so imagine that we go to Euclidean signature, is to replace this spatial slice by a closed three-manifold, right? So we can instead consider sigma 3, which is closed, and integrate the normal component of the current over sigma 3. And the same argument that told you that this Q is time independent, using current conservation and integration by parts and so forth, also works here. If you apply it here and you use current conservation, then Stokes' theorem tells you that deforming this surface sigma 3 by a little bit doesn't change this Q of sigma 3. So if you take...
What did you write? Integral J plus?
J per. This is, this is very unsophisticated. If you're more sophisticated, you can write star J. Okay. This is,
Why is this specific to Euclidean signature?
Why is this specific to Euclidean signature? Well, formally, this manipulation is possible in Lorentzian signature as well. But this closed three surface in Lorentzian signature is a little bit funny, since it kind of extends in the time and the space direction. So for example, it has closed time-like curves, has subcurves on the manifold and so forth. We generally stay away from these kind of things. I don't know how badly things would actually go wrong if you tried. So imagine that you deform sigma 3 a little bit, so that you have some cobordism from sigma 3 to some nearby sigma 3 prime, right, then the difference of Q between sigma and sigma 3 prime can be written as the integral of the divergence of the current over the form manifold that interpolates between sigma 3 and sigma 3 prime. And since the current is conserved, that's 0. So this operator is topological, meaning it is invariant under deformations, small deformations, assuming that the current doesn't hit any other operators or defects when you do this deformation. So it's topological as long as it doesn't cross anything. And that's important because when it crosses something, then interesting things can happen. All right. Now, when you have a U1 charge, this Q is typically all you need and typically all you discuss, but it's certainly possible to exponentiate this charge to get U1 valued symmetry charges, and that's a useful thing to do, especially in various generalizations that I'll mention in a second. So instead of considering Q, consider the operator U alpha, which is e to the I alpha Q, where alpha is an angle. So I'm assuming here that my symmetry really is U1. In other words, this alpha really is an angle, and that's in one-to-one correspondence with the statement that the charges of Q are actually integers. And these exponentiated Q's carry essentially the same information as Q itself. And because Q is, in my example, an abelian charge, they have the property that they obey the group law. And this is a very useful notion that generalizes in lots of nice ways. We'll get to the generalizations in a second. Now let's imagine that you have a local operator that is charged under the symmetry, like, for example, my phi field in the O2 model. But it could be any operator. Consider some O of x sitting here. It could be in Lorentzian signature. It could be in Euclidean signature. How do you figure out the U1 charge of O of x? Let's assume that O of x has some definite U1 charge, Q, and I would like to measure this charge. What's a way of doing it? Well, the most standard way of doing it is to think in Lorentzian signature and to take the commutator of the charge with the operator. That gives you, up to an I, it gives you the charge. Okay? So that's the most familiar kind of thing that you do in quantum field theory. But we can generalize this in a variety of ways using these Q of sigma 3s. For example, you can think of this commutator as essentially being a kind of situation when this sigma 3 is like a little sandwich, which maybe I'll explain in a second. Imagine that you're now switching to Euclidean signature and you take sigma 3 to be a ball or a 3-sphere surrounding this operator exactly once, linking this operator once. If you then evaluate this Euclidean Q on this sphere, then you will also evaluate the charge of the operator. Right? It also computes exactly that. Now, this Lorentzian commutator is a kind of degenerate limit where you take this squished sphere and you squish it into a kind of pillbox, where the upper half of the sphere is Q at a slightly advanced time, and the lower half of the sphere is Q at a slightly retarded time, and then you can make contact between this Euclidean picture and the Lorentzian commutator. Now, in the case of a U1 symmetry, where we also have a current, this Euclidean picture of surrounding the operator by this Q of sigma 3 has a nice local version, which is the OPE of the U1 current with the local operator O. So the fact that this sigma 3 integral picks up Q means that the divergence of the current has a delta function, Q times delta, at the location of the operator. And that's tantamount to the statement that the OPE of J with O has some kind of singularity going like Q over X cubed times O. Now I'm kind of suppressing various tensor structures here. I'm just writing the scaling. The current in 4 dimensions has scaling dimension 3. And so you can see that the OPE between J and O, which is non-local, which is a non-local universal piece of data, knows about this charge Q. And when you take the divergence of J, this 1 over X cubed turns into a delta function, which is responsible for giving you the charge Q when you evaluate the integral over this surface. So these 3 perspectives are all useful in different contexts. When you have a current, which you only have in the continuous case, the current algebra or OPE point of view is typically the most powerful because it gives you the most information. But the Euclidean Q of sigma 3 or U of sigma 3 is the most useful in situations where you do not have a conserved current.
Why is it X cubed? You're choosing a certain dimension of space?
Yes, I'm in 4 dimensions. J has dimension 3.
X mu divided by X cubed.
Yeah, I told you I was being sloppy about tensor structure. I should have written X mu divided by X to the 4th. Something like that. But I didn't want to do that. That's why there's a squiggle here. Very good. Now, as you probably know, you can repeat essentially all of these arguments for the stress tensor. Every single one of these different kind of ways of doing it has an analog for the stress tensor as long as you contract with a suitable killing vector. Now, when you go to discrete symmetries, of course, you do not have a conserved current, right? So that means that there's no J, and there's no Q, and there's certainly no OPE. But it turns out that even for discrete symmetries, the analog of this object survives, because this object is a topological surface defined for every element of the group, of the symmetry group. Here the symmetry group is labeled by alpha, but in general it could be discrete, and there could be a finite list of elements, finite or infinite list of elements. So for example, in the Z2 case, in the Ising case, you would simply have 2 topological operators, one corresponding to the non-trivial element of Z2 and one corresponding to the trivial element, and they would obey the group law. And they would be the only part of this structure that survives in the discrete case. Very good.
How do you define Q in that case?
You do not. I said it doesn't exist. Only U exists in that case.
Okay.
Other questions? Okay, very good. So of course, this is kind of the starting point. Now you can run and do all you ever learned about, global symmetries in quantum field theory using these things. You can do it for the internal symmetry J. You can do it for T mu nu, and you can get lots of nice and useful results. Now, given the utility of this kind of formalism or approach to symmetries, which I'm not demonstrating to you, I'm kind of just assuming that you have some example in your mind where you appreciate this, the importance of this, you might want to try and generalize it in a variety of ways. And kind of historically, there have been, of course, people were not ignorant of this fact. There have been attempts at generalizing the notion of symmetry, of global symmetry, for many, many decades. And there's a basic question that arises, which is kind of which avenue of going from an ordinary symmetry with a one-form current to something more general, you want to choose. And historically, the one that people had focused on most is the one that takes the natural generalization to be J mu for zero-form symmetries, and then T mu nu for ordinary spacetime symmetries, and then going from that to a situation where you have a current with many, many symmetric indices. Right? So one possible generalization would be to take a current that has lots of symmetric indices. Clearly, that's a generalization of the sequence, with J mu and T mu nu being the first two members of the sequence. These things are typically called higher spin currents. Right, they're in symmetric tensor representations of the Lorentz group, so they indeed have higher. They have Lorentz spin bigger than 2.
Are they associated to some symmetry group, like in the Poincare case or something like that? This higher form symmetry?
Well, it depends on a bit on the space-time dimension. There is a higher form symmetry group that is associated with these, which is extra complicated in 2 dimensions. It's a little bit less complicated in 3 or more dimensions, but it's still very rich. It contains an infinite number of charges and of all spins, an infinite number of currents of all spins with a rather complicated algebra.
But how this is compatible with the Coleman-Mandula theorem? Like you have more than spin 2 particles, like you need to couple?
Good. So Coleman-Mandula is the correct slogan, but it's not about spin 2 particles, which is also an interesting story, but it's about spin 2 currents. So this generalization is very rich and very interesting in 2 dimensions, in 2 space-time dimensions, where it arises in integrable theories. Integrable theories are precisely theories in which these kind of currents exist. And that's what's responsible for their solubility. But if you are in 3 space-time dimensions or higher, then indeed the Coleman-Mandula theorem, or an interpretation of what Coleman and Mandula said, is that theories that have these kind of currents would have trivial S matrices, would have trivial scattering. So they would essentially be free theories up to some possibly kind of global issues. Exactly. So of course there are nice sub-clauses and there's lots of fine print related to the Coleman-Mandula theorem. For example, there's supersymmetry and things like that, which they didn't consider. But this is only interesting in 2 dimensions, more or less. Unless you have a particular reason to be interested in free theories. I mean, there's contexts in which they're important. But if you're interested in interacting theories, this is only interesting in 2 dimensions. And in d greater than or equal to 3, Coleman and Mandula said that this J mu with many indices implies that the theory is free. They really said that the S matrix is trivial. It takes more work to prove that the theory is free if there is no S matrix. For example, if you have a conformal field theory with such currents, but that was done by Maldacena and Jeboyd of about 10 years ago or so, 15 years ago. All right. So this is a potentially very interesting generalization, but it doesn't work.
Thomas, you have a third blackboard if you need the... Where? There's probably a stick to like, bring everything up.
That's too sophisticated for me. Let's see. I mean, okay, put this all the way. I think getting it up is easy. Getting it down would be. All right. Well, but can people still see if I... Where's the stick?
No, I think it's still.
Okay.
Sorry, I didn't mean to make a.
Let's see. We'll try it, and if it fails, we'll stop doing this. All right. Reminds me of middle school. All right. Can people see if I write on this? This is a little bit dark. Yeah. Okay. Yeah. Sorry. This is when I betray my cultural heritage. D is the space-time dimension. Very good. Now, I'm not going to prove the Coleman-Mandula theorem for you. There are lots of nice proofs. For example, you can look at Weinberg, volume 3, very nice proof. But for this proof to work, it's essential that these higher spin symmetries act on local operators. They act on particles, right? The S matrix is the thing that tells you how particles scatter. And this symmetry highly constrains the S matrix to be trivial. So these higher spin symmetries act on local operators, and they act on particles. So the generalization that we're going to be talking about, the alternative route, is what are called higher form symmetries. And I haven't told you yet what they are, but in order to evade this loophole, you better make sure that they don't act on particles. Yeah.
On that connecting node between the higher spin symmetry and higher form symmetry, is it known that theories with higher spin currents don't have any non-local operators that are non-trivial in degraded?
No. For example, an example is free Maxwell theory, which I'll spend the rest of this lecture discussing, and there are many interesting non-local operators.
Yeah, exactly. But I'm talking about theories with higher spin currents. Not higher form.
Free Maxwell theory has higher spin currents. Okay. Many, because it's free. Any free theory has an infinite number of higher spin currents. Roughly speaking, because the momentum of every single particle is individually conserved. And that's what these higher spin particle symmetries express. All right, so we need something that doesn't act on particles. And it turns out that the correct generalization is to take a current that looks very much like this, but to take it to be fully antisymmetric in its Lorentz indices rather than fully symmetric. And this will solve all the problems that the higher spin currents have. All right, so that's what we'll get to. These are the higher form symmetries. And we'll take a little detour and start discussing Maxwell theory, and then I'll get back to why Maxwell theory has these symmetries and how they evade the Coleman-Mandula theorem. I mean, it's not completely obvious just from the tensor structure that they evade the Coleman-Mandula theorem, but maybe a clue that they're on the right track is that these fully antisymmetric currents do not have space-time spin 2 in any plane. They actually have bounded spin. All right. So one thing I should say at the outset also is I'll be discussing invertible examples of both zero form symmetries and higher form symmetries, and also their interplay via higher groups. But as you will hear from many other speakers, there are also so-called non-invertible versions of these symmetries where the operators that I wrote here no longer satisfy a group law, but they satisfy something more interesting. All right. Now, in order to kind of tether our discussion to a little bit of physics, I want to anchor what I'll be doing in some kind of physics context. So I'm going to be talking about 4 dimensions, as I already said, and I'm going to be focusing on gauge theories. And as I said in the beginning, gauge theories are interesting no matter where you come from. And in particular, I'm interested in the phases of gauge theory and how higher symmetries and the interplay of higher and ordinary symmetries allow us to organize what we know about the phases of gauge theories and also to say something new. All right, so for the rest of today, I think we will start with the most elementary example of a gauge theory in 4 dimensions, which is free Maxwell theory. And unless I sort of make a mistake or say explicitly otherwise, I'm going to assume that I'm in Euclidean signature. I'll occasionally say things about Lorentzian signature, but I kind of write formulas that are appropriate for Euclidean signatures. All right, so Maxwell theory is given by an action which looks like this. There's a gauge field, which I'll call A, with a superscript that I'll explain in a second. And then we have an integral over space-time of f wedge star f. I'll generally use these superscripts 1, 2, and so forth to generate forms, form degrees. So this A is a 1 form, f is a 2 form. F is the standard field strength. And by taking another d, using Poincaré's lemma, you get that f is closed. And if you take the equation of motion of A, you also learn that f is co-closed. So you get two nice equations, which are the free Maxwell equations. Now, this A here in the presentation that I'm giving is a standard U1 gauge field, a standard U1 connection. So that means that it has a gauge redundancy given by d of lambda 0, where lambda 0 is a circle-valued scalar field. So these are zero-form gauge transformations. Lambda 0 is a function from space-time to the gauge group. All right. So this being a standard U1 connection with periodic gauge parameter lambda, there are quantized fluxes. So if you take the integral of f on any.
Yeah. Question? Yeah. Is it written now? Shouldn't it be to the algebra, not to the group? To the group, it should be lambda to minus 1 d lambda, I guess.
It should be as I wrote it. So lambda is periodic. The Lie algebra is R. Lambda is periodic.
And your gauge?
You can. The gauge field does take values in the algebra, yes.
Well, I think there is a question of what is U1 for you? Is it R mod Z or is it?
There's some implicit isomorphism that I'm using that I'm not going to say anything about because I'll probably say it wrong. All right. Other questions? Right. So because lambda is not necessarily single valued, because lambda can have jumps by 2 pi, right? That means that d lambda can have winding around closed curves, and that's what leads to the possibility of quantized Dirac fluxes. So if you take the integral of the flux over a closed 2 cycle, sigma 2, then this number, 1 over 2 pi times f, has to be an integer. So one way to see that, if you take, for example, sigma 2 to be a sphere, is that you can evaluate this flux by using Stokes' theorem, and then you get the difference of A in the northern hemisphere minus the southern hemisphere integrated over the equator. This difference is precisely given by a gauge transformation d lambda, and so that difference is really the winding number of this gauge transformation, and that has to be an integer. So that's the Dirac argument for quantized flux.
Sure, just a question of conventions. Are you taking A to be a globally well-defined one form, or are you taking that
A is a U1 connection? A is a U1 connection.
Okay.
Otherwise, it wouldn't have flux.
Is there like a similar one-line argument for quantized flux on any 2D surface, or do you just have to kind of just say that's some math theorem?
Well, I think there's a similar argument because you can do more complicated cuttings, right? So you can always cover every surface with some nice patches. Then you can cut open along all the patches. You'll get the integral of the differences of A along the boundaries, and then you can relate it to some winding numbers. This is a very cumbersome way of doing something which comes out of some fact about the fact that this is a kind of Chern class, which is naturally an integer. Some sort of check description of the first Chern class. All right. So one comment, which is just a small comment here, is that in elementary presentations, of course, you typically don't discuss the gauge coupling in free Maxwell theory, but here, because we have already put in the global information that the fluxes of F are quantized, it doesn't make sense to rescale this gauge coupling, because if you do that, then you can do that. There's nothing wrong. You can always change your field basis, but if you change your field basis, then the quantization condition for F will also change. Then the gauge coupling will appear here. So this theory actually knows about its gauge coupling, and E is a meaningful parameter of the theory. Very good. So this theory has a few zero-form symmetries, which I'll not spend too much time on. Of course, it's Lorentz invariant, so it has a conserved stress tensor, T mu nu. It also has a few discrete symmetries, C, P, T. If you don't add a theta angle, which I haven't done, there's C, P, and T. And we won't need them that much, so I won't say too much about them. One thing that I do want to say is that any Lorentz invariant theory, right, any theory that has a conserved stress tensor can be coupled to a metric. If you're in Lorentzian signature, it's a Lorentzian metric. If you're in Euclidean signature, it's a Riemannian metric. But you can take this action, you can generalize it to curved space or curved spacetime. And you can consider these theories on suitably nice Lorentzian and Euclidean four manifolds. And that's a very useful thing to do. That's the kind of analog of turning on background fields, but for spacetime symmetries, right? And so studying partition functions and observables on such curved backgrounds or such non-trivial backgrounds is a very useful thing in general, and especially if you're interested in anomalies and their consequences.
Thomas, can I ask a question? Yeah. So the equations that you wrote on the blackboard, are these the equations? Some of the equations are classical equations, some of these probably are quantum equations. Can you say more about this?
When you say classical and quantum, do you mean off-shell and on-shell?
For example, that equation on the left, the fact that the fluxes are Z. Is this a classical equation, or do you want to promote it right away to a quantum equation? Can you say something?
This is a classical statement about U1 connections. Every single configuration in the path integral satisfies this.
So there's no quantum thing here at the moment?
Well, this is an equation of motion, but yeah, even that's classical. Mm-hmm. Very good. Let's see how much time I have left. Oh, great. I'm doing very well. All right. Let me say a few words about electric magnetic duality, which is an important property of Maxwell theory. It will simplify various pieces of the presentation for me. I'm sure other people will refer to it. So I thought I'd briefly remind you of that. And incidentally, even though I won't have time to emphasize it, but maybe a comment I should have made in the beginning is that Maxwell theory is kind of two higher form symmetries, the analog of the compact boson in 2 dimensions for zero form symmetry. So there are very many parallels between those two examples. And I won't have time to kind of flesh them out, but I encourage you to flesh them out for yourself. So almost every single thing that I say about Maxwell theory has an analog there, including electromagnetic duality, which becomes the T duality, the R to 1 over R duality of the compact boson. All right. So what's electric magnetic duality, or S duality? Well, roughly speaking, it's a change of the presentation of this theory where we switch from using the electric degree of freedom A, and we trade it for the magnetic dual gauge field, which is not visible here, and we're going to, in the process, switch electric and magnetic fields up to some minus signs. And we're also in the process going to switch these two equations around. So I'm not going to give too much detail, but let me give you a super quick rough sketch of how you derive electric-magnetic duality. The trick, and then I put a longer exercise for the exercise session in the afternoon where you can do this in all dimensions, kind of for all abelian p-form gauge theories. The starting point is always to take this constraint, or whatever its analog is, and to trivialize it using some Lagrange multiplier. So instead of taking this constraint here is an inevitable consequence of the fact that f is dA, where A is a U1 connection. So the first step is to relax this and to view f as just a garden variety 2 form, not necessarily related to any A. But then you have to impose this flux quantization condition by some other local means, and you can do that using a Lagrange multiplier. So you would take the following presentation. So this is now a different action, a superficially different action. Let me call it S tilde as loaded as whatever, something else. So this piece looks exactly like the Maxwell action, but f is no longer dA. F is just some 2 form. It's no longer closed, and it doesn't have quantized periods anymore. And instead, I'm going to introduce a Lagrange multiplier, which I'll call A tilde, and then the following coupling of A tilde to F. So this is an action which depends both on A tilde and on F, but not on A. There's no A inside. This A tilde, however, is a garden variety U1 connection, but for a different gauge group. Let me call it U1 tilde. So this A tilde will turn out to be the magnetic dual gauge field, and U1 tilde will be the dual magnetic gauge group, which has absolutely nothing to do with this U1 gauge group acting on A here. So this will be a baby example of what I said at the beginning, which is that we'll have a theory where the notion of what the gauge group is ambiguous. We'll have one presentation where it's U1 and one where it's U1 tilde. And there are many others, infinitely many others. All right. So this U1 tilde connection satisfies the same properties as any U1 connection. There's a gauge redundancy, and the gauge parameter, the lambda tilde parameter, has an integer winding number. And now, the first thing I want to claim is that the quantum theory based on this action, if I do the path integral over A tilde and F, is the same as the quantum theory based on doing the path integral over A here. How do you see that? Well, when you do the path integral over A, notice that A doesn't appear quadratically in this action. A only appears linearly. So it only appears in this term. It's a Lagrange multiplier. This term is a glorified Fourier transform in field space, and this is like a kind of Fourier representation of a delta function. And the delta function will set df to 0, first of all. That's easy to see, because if you take the equation of motion for A tilde, if you vary with respect to A tilde, you can integrate by parts, and you get df equals 0. But more than that, A tilde is not just a 1 form, it's actually itself a gauge field, and that means that A tilde has quantized fluxes. F doesn't, but A tilde does. And when you also sum over these quantized fluxes, that gives you a kind of discrete Fourier transform, or a discrete Fourier representation of a delta function, and that will ensure that F is constrained to have integer quantized fluxes like this. So integrating out A tilde over there reproduces this. in the path integral. Notice that it's very important that we do the path integral over everything, right? These two actions are not the same in any obvious sense, but the path integrals are the same. All right, so this is point number one. So this theory is equivalent to this one, but now we can do something else. Let's see, maybe I should switch things around a little bit. Okay, now we're going to get into trouble.
Bye-bye.
Yeah, it's coming back. All right, so integrating out a tilde here reduces me to that. Now the final step is to do the integrating out in a different order. Instead of integrating out a tilde, let me integrate out f. That's easy to do. F is a completely unconstrained two-form, and this is a Gaussian theory. So integrating out just means evaluating by saddle point. You compute the equations of motion of f and plug it back into the path integral. What are the equations of motion? Well, they tell you that I over e squared star f is 1 over 2 pi f tilde, where f tilde is the dual magnetic field strength dA tilde. This is the saddle point equation coming from here. This I is necessary in Euclidean signature for all sorts of reasons. It's first of all necessary to get the kind of Fourier representation I was talking about, but it's also compatible with the continuation to Lorentzian signature, because in Euclidean signature, any term that has an epsilon symbol needs an I. Right? And if you expand out this wedge, it has an epsilon. So this leads to this very regrettable but important factor of I in the saddle point equation. This factor of I is not there in Lorentzian signature. In Lorentzian signature, this equation would say that the real electric and magnetic fields get swapped. And in Euclidean signature, you have to deal with this annoying I, basically because the electric field is naturally imaginary in some way of thinking about things. All right. So when you plug this equation back into this action, then you get S tilde, which is a function of A1 tilde only, and it will look exactly like the free Maxwell action written in terms of F tilde, this one, with a dual gauge coupling, which comes from plugging in this formula for F, right? And because of the usual yoga of Gaussian integrals, when you evaluate on the saddle point, this e squared jumps from the denominator to the numerator. So this dual gauge coupling, e tilde squared, is 4 pi divided by e squared. So we have a physically equivalent presentation derived using elementary manipulations of Gaussian path integrals, where now we have formulated the theory in terms of a dual magnetic gauge field. The gauge coupling has changed, and the electric and magnetic fields have changed. Yeah?
So I can view this like the action that you wrote over there. I can view that as just usual Maxwell coupled to an EF theory.
No, because usual Maxwell would have an F that is itself dA. This is not that. This F is not dA. This F is unconstrained. Yeah.
Is there something that tells us what groups can be dual to what group?
Yeah, in the abelian case there is. So I told you that the gauge group is U1 and the dual gauge group is also U1, which is true. But the dual U1 is supposed to be the Pontryagin dual of the original U1. Is there another question somewhere?
Yeah, but Pontryagin dual of U1 is Z. How is that possible?
Isn't it supposed to be the Langlands dual?
Yeah.
Maybe it's the Langlands dual for the gauge group. Yeah. Okay, what else did I want to say about this? Hold on. There are a couple of important points here that I don't want to miss. Right. So we're almost at the point where we can talk about one-form symmetries, but I want to make an important comment before about what the status of this operation that we've performed. So what is this S-duality? The way that I've derived it, you see, it's just a rewriting of the theory. You have two equivalent presentations of the same functional integral, and they describe the same physics. So generically, unless you are at some special point and there's a special story, but generically you should think of this duality operation as being really a redundancy in the description. And very much analogous to the gauge redundancy that I talked about in the beginning, but a little more sophisticated. So gauge redundancy is you have a gauge group and you mod out by gauge transformations, and therefore your different gauges are equivalent presentations of the theory. Here also different S-duality frames are different presentations of the same theory. The only exception to this statement is at the special point where the dual gauge coupling is the same as the original gauge coupling, and then it turns out that S-duality acts like a genuine zero-form symmetry on the theory. And then there's a kind of nice non-invertible generalization of the statement that I just made, but generically it's just a redundancy. There was a question somewhere? Yeah.
Can we write down an action which is symmetric in A under duality?
Yep. You can, but you cannot do it in a manifestly Lorentz invariant way. So there's a... Yep, you can do it in a gauge invariant... Well, you should never ever do things in a gauge non-invariant way, ever. Don't even think about it. But you can do it. So these kind of actions for Maxwell theory were written down by Sen and Schwartz in the early 90s because they were interested in studying the self-dual phi form of string theory. But there's a nice version of that in 1+1 dimensions where you can write the compact boson in a way that's manifestly T-duality invariant, which is the kind of Luttinger presentation. But that's a kind of non-Lorentzian invariant theory where you explicitly need to write dt and dx of various fields, and so you need to pick a Lorentz frame. The theory is Lorentz invariant. You can show, but it's not manifestly Lorentz invariant. That's right. Yeah. So you can do the same thing here. Other questions? All right. Very good. So now we can finally talk about one-form symmetries again. Remember I told you that eventually we're going to get back to higher form symmetries associated to totally anti-symmetric conserved currents like that. And Maxwell theory provides you with probably the simplest example of this for the case of a one-form symmetry. So in general, let me say that a p-form symmetry a continuous p-form symmetry is associated with a conserved p+1 form current. So there's a J there with p+1 totally anti-symmetric form indices, and it's also conserved. So there's an off by 1 which is introduced in the definition here, which is a little bit like the off by 1 of D-branes. One has to get used to it. It's a little bit annoying, but a p-form symmetry is associated with a conserved p+1 form current. Now, so this is the general definition, and Maxwell theory very nicely furnishes us with an example of the simplest non-trivial case, which is p equals 1, one-form symmetry. Now, why is this so? Well, essentially because of the two Maxwell equations that I wrote up there. df equals 0 and d star f equals 0. F is a two-form, and then star f is also a two-form in 4 dimensions. So we have two closed two-forms, and that also means that we have two co-closed two-forms. So in fact, we don't just get one-form symmetry, we get two. An electric one and a magnetic one. So you can, in principle, normalize these currents any way you want, but it's nice and sensible to normalize them so that the corresponding charges are quantized in integer units. And in those units, the electric one-form symmetry needs a factor of the gauge coupling here, and the magnetic one-form symmetry current needs a factor of 1 over 2 pi times f. And the corresponding conserved charges are obtained by integrating star of these currents over something. Remember that in the case of a zero-form symmetry, we integrated star of j, j was a one-form, over a 3-cycle. And now we have two forms, Jm and Je, and their stars are also two forms. And so the thing that we can integrate these over is a closed 2-cycle. So the corresponding electric and magnetic charges are obtained by integrating f and star f over closed 2 cycles. So you recognize immediately the magnetic charge here as the integrally quantized magnetic flux from up there, and the electric one-form charge is the electromagnetic dual of that. It's the quantized electric flux. So this is the properly quantized kind of electric field whose Gaussian flux integral on a 2-cycle counts the charge inside. These are just Gaussian flux integrals. Just evaluating E perpendicular and B perpendicular on some closed surface sigma 2, and you know that integrating them gives you the total electromagnetic charge inside. And you can see from the equations I wrote up there about how the action of S duality on the electromagnetic fields that S exchanges QE and QM with some minus signs. So QE goes to QM and QM goes to minus QE. Very good.
Yeah, so in this free max field, where is the charged object?
Very good. We'll get there in a second.
Background.
We'll get there in a second. Yeah. There are no dynamical charged particles. There are no charged fields.
Yeah. Maxwell theory.
But, and in fact, that's essential, as we'll learn very shortly. The fact that these things are conserved essentially depend on the fact that there are no charged fields in Maxwell theory. But there are still charged operators. And so we'll discuss them in a second. Yeah. Very good. And then if I wanted to, I could easily exponentiate these charges to get the analogs of these U's. These U's would be labeled by angles. These are U1 one-form symmetry. There's a U1 one-form symmetry which is electric, and a U1 one-form symmetry which is magnetic. So here I'm denoting also the symmetries by superscripts to remind you that this is a one-form symmetry. And the symmetries are U1 because these charges are integers. We'll see that in a second explicitly. And when you exponentiate them, you get topological operators that live on closed 2 surfaces and that satisfy the U1 abelian group law. So there are a couple of important points I wanted to get back to. The first point, remember that I promised you that there would be a good reason why these symmetries evade the Coleman-Mandula theorem. And the reason has to do with the fact that they're totally antisymmetric form currents, and the corresponding charges live on these lower dimensional manifolds. They live on 2 cycles rather than 3 cycles. So think about a point particle, right? Think about a point particle living in 3-dimensional space. It sits somewhere in that space and it carries some charge, some zero form charge. It could be a particle that's created by some field like phi. Now when you integrate the zero form charge over the entire spatial slice, you necessarily cross the location of that particle because you're integrating over all of space. So you have to pick up the charge of that particle. And that's why the zero form symmetries always act on particles and local operators. But that's not the case for one form symmetries, right? One form symmetries are topological object of 1 dimension lower. So that if you have a particle sitting somewhere in R3, the corresponding Gaussian flux integral actually doesn't sit anywhere in R3, it sits at infinity in R3. You know that if you want to measure the total electromagnetic charge in R3, you should compute the Gaussian flux integral at infinity. And in fact, that's the only non-trivial place where you can pick up flux. And that means that that flux integral doesn't ever cut the location of the particle, right? So that means that the flux integral at infinity and the operator that created the particle, the local operator that created the particle, commute, and the particle cannot carry one form charge. We will see in a second, that was your question, what the charged operators and also the charged dynamical excitations are that are charged in the one form symmetry, and we'll see that they're both extended. They're not point-like. So this is how you evade the Coleman-Mandula theorem. These symmetries simply do not interact with the S matrix at all, with the standard S matrix for particles. All right. A second comment is that very closely related is that because these topological operators live on surfaces of dimension 2, you can always slide them past each other in Euclidean signature. That's not the case for codimension 1 surfaces, which have a natural ordering, and you can't slide them past each other without crossing. And that's roughly speaking why zero form symmetries can be non-abelian, because there's a difference between the orderings. But the higher form symmetries do not have this notion. You can always slide them past each other, and therefore they're always commutative. They're always abelian. We will see generalizations of one-form symmetries to other gauge theories, in particular to non-abelian gauge theories. We'll discuss that tomorrow and on Wednesday. And in those theories, there are all sorts of one-form symmetries, but one important class of one-form symmetries is related to the so-called center symmetries. These are related to the center of the gauge group. And the analog of that center symmetry in Maxwell theory is this U1 electric. This U1 electric is really, well, it's the center of the gauge group. The center is the whole gauge group because it's abelian. So this is what you should think of as center symmetry. This dual magnetic symmetry, you can think of it as the center symmetry of the dual gauge field. Notice that the notion of a center symmetry depends on the notion of a gauge group, and therefore it's not duality invariant. Okay. So let's get to the question of what are the charged objects under these symmetries. Well, we learned over here that the charged objects, the point operators, are supposed to be linked by these topological 3 surfaces, right, that can link non-trivially with a point in Euclidean signature. And there's a natural analog of that for higher form symmetries, in particular for one form symmetries. Now the flux operators live on 2 cycles. So you can ask, what are the objects that naturally link with 2 cycles in Euclidean signature? And so if we're in 4 space-time dimensions, imagine a simple 2 cycle like a sphere, that links a loop, a line in 4 dimensions. Okay? So we should think about the line defects, the one-dimensional defects of Maxwell theory. And indeed, there are many interesting such defects. All right, so let's discuss them. Maybe I'll do it here. The probably most familiar class of such defects are the Wilson lines and the Wilson loops of the theory. So a Wilson loop or line, it's a loop or line depending on what exactly the curve is that I'm going to define them on. I'm going to take a closed curve C in Euclidean signature, in my Euclidean four manifold, and then I'm going to define W to be the Wilson loop of electric charge QE. This is simply the exponential of e to the I QE, and then the holonomy of A along C. And the words one typically says is that you should think of this Wilson line as the world line of an infinitely heavy kind of external probe particle, non-dynamical probe particle of electric charge QE, which has a prescribed trajectory C that you engineer by hand by dragging the particle around. So we are not adding dynamical particles to the theory. This is just some operator in the theory, some defect in the theory. By the way, in relativistic theories and Euclidean signature, there's no distinction between operators and defects. So I'll kind of use them interchangeably. If you're a non-relativistic person, then you need to be more careful. All right, very good. And gauge invariants, in particular large U1 gauge transformations, require the electric charge here to be quantized in integer units. All right. And if you surround this Wilson line with a, where's my electric operator? If you surround this Wilson line, link this Wilson line with a two-dimensional electric Gaussian flux surface, you measure the electric charge inside. So the way you should think about this is that C is the world line of the particle. So the particle is traveling along C. This is roughly speaking time, Euclidean or Lorentzian time. If you look at a moment in time, if you cut a time slice and you blow that up, that's actually R3, right? So at a given instant in time, the particle sits somewhere in R3. Let's take it to be the origin. So it's a kind of charged, electrically charged object at the origin here, and then you're linking that point with a two-dimensional Gaussian flux integral to evaluate the charge. Right. And it's easy to do an explicit computation using commutators that tells you that this is the case. All right. So these are the electrically charged operators, operators that are charged under the electric one-form symmetry. Very good. Any questions about this? All right, so let's discuss the magnetically charged ones. By electric-magnetic duality, we sort of know that there has to be a magnetic version of everything. So if we could just apply electric-magnetic duality to this, we would immediately say that you should replace A by A tilde. Then you get the magnetic Wilson lines, and you should replace QE by QM. But there's a way of saying that even in the original duality frame, which is that you can introduce what are called the 't Hooft lines directly in the original presentation. Of course, they will turn out to be the dual magnetic Wilson line. So 't Hooft lines, one way of thinking about them is Wilson lines of A tilde, so in the dual presentation, let's call them H for a 't Hooft, and the 't Hooft line of charge Qm can write as a Wilson line for A tilde. But if you want to give a description in the original duality frame, what you can do is you can take the curve C, right, and then you can define this 't Hooft line by requiring that, right, if you look at a small neighborhood of this curve, a tubular neighborhood of this curve, it looks exactly like the blow-up that I drew before. Right? If you take an instant of time here, this looks like a little sphere inside R3. And you can simply demand that the magnetic flux across this sphere should be Qm. Right? So this is a valid choice of boundary condition. If you drill out the small tubular neighborhood from space-time, right, then you now have a manifold with a very small tubular boundary, and you need to impose boundary conditions to have a sensible field theory. And this is a valid choice of boundary conditions, which defines the 't Hooft line. And then you take a limit in which the size of this tubular neighborhood shrinks to 0. So this 't Hooft line is a quintessential example of a disorder operator. It's kind of the analog of a monopole operator in 4 dimensions, the analog of a winding operator in 2 dimensions. So there are many, many analogs like that. And of course, by virtue of being defined by this boundary condition, it's almost tautologically true that this line is magnetically charged and has magnetic charge Qm. Is there a question or no? Very good. So we have electric lines charged under the electric symmetry, magnetic lines charged under the magnetic symmetry. You can get lines with arbitrary electric and magnetic charge called dionic lines or dions by fusing these lines, and then you'll get lines that carry both charges. The one thing you have to be careful about, which is very interesting, is that when you fuse electric and magnetic lines, there's a kind of Dirac angular momentum between them, which can sometimes turn them into fermions. Roughly speaking, in the most elementary presentation that I gave here, both the electric and the magnetic lines are bosons, meaning they have standard statistics. You move them around each other. But for example, if you fuse a charge 1 electric line and a charge 1 magnetic line, then there will be a half integer unit of Dirac angular momentum, and you get a fermion.
When you say fuse, is it a dynamical process?
No, fuse as in OPE. Like these are all operators. There is the dynamics of the theory is free. The theory is boring.
Well, I'm boring, of course. I've been talking about it for a long time, but it's elementary. Is the sophisticated way of saying that.
Okay. Now, let me sort of get to the main slogan that I want to get to about the kind of physical intuition behind these electric and magnetic one-form symmetries. Right? So these things are conserved, they're topological, you can move them around, and they measure by linking the electric and magnetic charges of these lines, these electric and magnetic lines. That means that the electric and magnetic fluxes carried by these lines can never terminate. They have to keep going forever. If they ever terminated, right, then you could take this allegedly topological surface and slide it off the end of the line. Right? Imagine that you could terminate the electrically charged line somewhere here. You're measuring your Gaussian flux. It's topological, so you can move it around. You move it here, you move it here, you move it here, and then you slide it off. And then it becomes trivial. So if that were the case, then this symmetry could not be topological, or equivalently, the line could not be charged. The only way to have charged lines and these topological two surfaces is if the line can never end. And since the flux, you should think of the conserved quantity associated with this never-ending line as being flux. It's either electric flux or magnetic flux. So this is a very sophisticated statement of the Gauss law for electric and magnetic flux. And the way you should think of the one-form symmetries, at least in this problem, is that they're flux conservation symmetries. And this point of view will be easily generalizable to many other contexts. And of course, one of the things that we'll discuss tomorrow is that if you add either electrically or magnetically charged matter, then some or all of the lines can actually end, and then some or all of these symmetries will actually disappear. Okay, any questions?
Can we talk about toothed loop?
I talked about it here.
Yeah, but you're saying it said 9 never ends.
Also never ends.
Something maybe a bit more broad. So the conservation of these currents, at least in this particular example, is somehow a consequence of F being closed or F tilde being closed, which in some sense relies or has to do with gauge symmetry, right? So
does it?
Well, I mean the fact that F is exact, or rather, the fact that F is exact means that it has a gauge symmetry. That A has a gauge symmetry.
That's in the electric presentation.
Right, but I mean, you could do it works for one of them, and then you could do the dual, and then you get.
So in one presentation, one is quote unquote because it's a gauge symmetry, and the other one is not, and then you switch it around in the other presentation.
I guess.
And I think the symmetric point of view is that neither of them are due to a gauge symmetry.
Okay.
I tried to discourage you from thinking too much about gauge symmetry.
Right, because where I wanted to go was it seems in some sense that this one-form symmetry is somehow inherited from the zero-form symmetry.
Well, there's no zero-form symmetry. I haven't gauged anything.
Right, yeah, no, it's not global.
You're trying to think of this as coming from gauging something, but a free Maxwell theory. So I gauged the empty theory. So the way that I would try to say it is that F and star F are gauge invariant operators, and they make sense. You don't have to commit to any presentation, A tilde. If you want to actually do computations, you pick A tilde, you do what you must, right? So of course we know that gauge fields are useful for all sorts of things, but at the end of the day, they're correlation functions of Fs, correlation functions of Fs with lines, and they're completely gauge invariant. And so we have two of these conserved currents here, and that's why we have two symmetries. What I said before about the center symmetry is a little bit of a rephrasing of what you just said, which is that in any gauge theory without matter, it's always true that there's a one-form symmetry associated with the center of the gauge group, and this is roughly speaking this one. But that's neither the whole story nor is it necessary. For example, just as an example, there are non-gauge theories. Can you give you a simple example? That have these kind of continuous one-form symmetries, and they have the corresponding conserved currents, and there are no gauge fields whatsoever. Let me give you an example. You can take the CP1 sigma model in 4 dimensions. So target space is a sphere. It has a closed two-cycle, and there's a closed two-form, which is the area form of the sphere, pulled back to space-time. So that satisfies D of that two-form is 0. Therefore, it's a two-form current for a one-form symmetry. The one-form symmetry is associated with winding from space-time to the CP1 target space. So the analog of a 't Hooft lines or Wilson lines, the charged operators under the symmetry are the kind of line defects that have non-trivial winding in the transverse S2.
So the symmetry is in some sense, it is fundamental.
Yep.
It's not like inherited from anything else. Good, thanks.
Or it might be inherited from two things. Yeah. Yeah, it passes. Yeah. Should we stop now, or do I have 2 more minutes? Well, maybe I'll just leave the 2 more minutes for questions, because I was about to start a new topic. Yeah.
So usually for the zero-form symmetry, when we see there's a symmetry, we need the Hamiltonian commute with the symmetry generator. So since the free Maxwell theory has a one-form symmetry, so you have a Wilson operator commute with the Hamiltonian line?
No, not the Wilson line. These charges commute with the Hamiltonian. These are the symmetries. The Wilson line is not the symmetry. The Wilson line is not even topological. The Wilson line actually depends on what choice of C you make. So the Wilson line doesn't commute with the Hamiltonian, but these fluxes do.
I was just going to elaborate on that point. Even though the U1 electric symmetry doesn't come from anything, the U1 magnetic comes from gauging like a Z1 form symmetry, right? If you consider our gauge theory, and I gauge a Z1 form group, or like a Z group, then I get the magnetic symmetry from the Pontryagin dual.
But that's one of a large number of ways of getting this symmetry. So in any presentation of the theory that you like, the symmetries have to be there. This is one of their virtue. So if you and I have different presentations of the same theory, we better agree on all the gauge invariant things, all the symmetries, all their correlation functions, all their charges of the charged operator. So, but I would not say that this one or that one is superior in any sense. You're typically forced into one particular presentation by the type of problem you study. So you may encounter it in one presentation or the other.
Yeah. Question. Last question.
Okay, so when you try to generalize the currents, we are talking about two extreme cases, like totally unsymmetrized and totally symmetrized. What are the intermediate? Like when I have some mixed young.
Yeah, it's kind of, it's not, I don't know if the answer is known in a completely uniform way. People have looked at this in special cases. It becomes very dimension dependent. Generally speaking, in some rough sense, whenever you have a current that has a spin projection in some plane that is bigger than 2, you are in the kind of higher form case, and in some cases there are no-go results for those kind of currents as well. But I would say that this hasn't been completely uniformly and generally stated and understood.
Yeah, because I imagine that when you have some antisymmetrization, the spin of the current decreases.
That's right. That's right.
Okay. Thanks.